In linear regression, we're going to calculate the best fit line that can be drawn through a combination of points that are made by xy pairs. And then we can use the equation for that line to predict values of y given a certain value of x. So we have an equation that your book uses, which is y equals b0 plus b1x. Your TI-83 calculator uses the equation y equals a plus bx, but as long as you just remember that the slope is the number that's next to the x and the y-intercept is the other number that's by itself, you should be okay no matter what letter gets used to describe it. Just a quick note over on the side here, the population slope is a big letter B called beta. It's a Greek letter, just like any other population notation. So for our hypotheses, we have the null hypothesis is that the slope equals 0, or you could use beta equals 0, and the alternative hypothesis is that the slope is not equal to 0 or beta is not equal to 0. The first example we're going to do is if we only have sample data. So if we're not given actual values of x and y, we're only given the mean and standard deviation of two groups and the correlation coefficient. We can still calculate the slope and intercept with those numbers. So you can see the equations that are here. So to calculate the slope, we take the correlation coefficient, r, times the standard deviation of y divided by the standard deviation of x. And for the intercept, we have the mean, sample mean of y, or y bar, minus whatever you just calculated for the slope times the sample mean of x, or x bar. So I have an example here. It says that data from caribou herd, which we're going to define as x, so caribou herd is x, and wolf pack we're going to describe as y, and we have sizes for both, in a region resulted in the following statistics. So we have x bar, or the sample mean of x, is 25.14, and the standard deviation of x is 5.81. For wolf packs, we have a sample mean, or y bar, of 62.57 and a standard deviation of 10.16, and we know the correlation coefficient is 0.915, and it needs to be significant in order to use that, so we'll say that it's a significant positive linear relationship between caribou herd and wolf pack size. So we need to calculate the slope and intercept for our linear regression equation. So remember, slope equals r, which is 0.915, times the standard deviation of y, which is 10.16, divided by the standard deviation of x, which is 5.81. And when you multiply all that out in your calculator, you should get 1.58. So there's our slope. Our intercept. Intercept equals the mean of y, which was 62.57, minus the slope that we just calculated, 1.58, times the mean of x, which is 25.14. And if you were to plug all that into your calculator and solve, you would get that the intercept is 22.85. So now we have both of the numbers, we can write our linear regression equation. Y equals the intercept plus the slope times x. Okay, so we have our equation calculated just by using the means and standard deviations of our two groups and the correlation coefficient. All right, so once we have a line for our linear regression equation, we can predict values of x given y, or values of y given x. Okay. So if we take this equation that we just calculated and we wanted to know if the caribou herd size was, let's go back up and look at our data. Let's scroll back up. If the mean of the caribou herd is around 25, let's just say we want to know if the caribou herd size was 30, how big would the wolf pack size be, which would be y. So you could plug in y equals 22.85 plus 1.58 times 30, and you could solve for y. Okay, so that's what we're getting at in this next part. I'm not actually going to solve that equation. I just wanted to show you an example. Okay. So you can plug in a number for one and calculate the value of the other. So the only times you should do that, we have to have a linear relationship. And you can check that by looking at a scatter plot. And that's something that you should do at the beginning anyway. If you're given values of x and y, before you even start doing correlation or regression, make a scatter plot to find out if it's linear. You need to have a value of r that indicates a linear relationship, which means it needs to be significant, which means the p-value for that correlation coefficient needed to be less than alpha. And the third one is you can't go too far outside the values of x and y that were used to calculate the slope and intercept. So let's just say, for example, we'll just say that x goes from 0 to 50 and y, we'll say y goes from 0 to 10. And we have some points that are given as our data set. Okay. And we've calculated a line for our linear regression equation. And we'll say that the question asks, what is y if x equals 30? We can do that because 30 would be within the range of data that was provided originally for x in order to calculate this line. So yes, we can calculate that. If it asks what is y if x equals 75, 75 is way out here, and we don't have any values that go that far for x. Our x's only went from 0 to 50 to calculate the line. We don't really know. We could maybe make the assumption that this line would continue as a straight line, but we don't know that. It's possible that the line could do something else once it gets out there. Let me grab a different color. So the line could start doing some kind of log increase. You never know, you could actually start going back down. So you should not use an equation to predict values outside the range that you're given, because you're not really sure what the line looks like outside what the range that you're given. So again, we don't really know what the line might look like beyond those values of x that we used to calculate our equation. So always check that. When it asks you to predict a value of y given x, make sure that x is within your range, or at least not very far outside the range. Our example for regression is using the same data set as we used for correlation. So if you still have that in your calculator, we'll continue to use it. The requirements are the same as for correlation. So we had the simple random sample, normal populations, XY pairs, and scatter plot showed that it was linear, and we checked for outliers, and we know that we have an outlier in our data set. So let me circle that one again. Okay. Our hypotheses are very similar to what you did for correlation. We're going to use beta for the slope equals 0. And for the alternative hypothesis, it's not equal to 0. You could also just write the word slope equals 0 and slope is not equal to 0 for your hypotheses. And now we're going to go back to our calculator and use the linear regression t-test, except now we're going to mainly be interested in A and B so that we can write our regression equation. Okay. So going back into the list, you'll see that I have the original list with the outlier still in it. So we're going to calculate our regression equation with the outlier first, and then we're going to do the same thing again without the outlier and have both equations next to each other. So we're going to go to the stat menu and tests and linear regression t-test. X's are in list 1, Y's are in list 2, frequency is always 0, not equal to for our alternative hypothesis. You can leave this blank, you can just use the equation that, or the equation format that the calculator gives you and calculate. Alright, so here's our output. Again, you can check which is the slope and which is the intercept. If you ever get confused, your calculator gives you the equation right here. So you can see that B is the slope because it's next to the X, and A is the intercept because it's by itself. The p-value tells you if the slope is significant or not, just like it told you if the correlation coefficient was significant or not. So you can see that our p-value is small. It's got the 10 to the negative fourth at the end. So we have a significant p-value. It's going to be less than alpha. And now the numbers that we need are A and B. Okay, so A is 20.14 and B is 59.08. And A is the intercept. Okay, so for our equation with the outlier, I'll just write them over here. So with the outlier still in, we get Y equals 20.14 plus 59.08x. And let's see. So for a conclusion, we can also say here, just like for correlation, we're going to reject the null hypothesis, and we can just say the slope is significant or the slope is not 0. Okay, so that means there is a linear relationship, and in this case it's positive. Alright, so let's do the same thing, except remove the outlier. So if we go back to our data, remember you can just highlight the one that you want to get rid of and push delete, and then make sure you do that in both lists. So now the outlier is removed. Go back to stat and tests and linear regression t-test. All this information should be the same as we just used. We'll go down to calculate. And again, the p-value is also significant. It's even smaller now. The t is bigger. And the numbers that we want right now are A and B. So 29.57 and 44.58. So we have Y equals 29.57 plus 44.58x. So again, we're doing the regression equation with and without the outlier. We're not sure if it's a mistake or not, so we can't really just get rid of it and go without the outlier. But this will probably be the more accurate equation for making predictions. So we're down to number 5 here. We're going to plug in the values of x. So in problem, after you find the linear regression equation, it asks to predict the values of y for x equals 1 and x equals 2. Okay. So for x equals 1, remember you always have to check to make sure it's within the range that's given for x. So you can see that x goes from, let's see, the smallest value of x looks like it's about 0.4, which is that one. And the biggest value of x, it goes up to 1.4. So 1 is within that range. So we can definitely make a prediction for y when x equals 1. So y equals, and we'll predict with both equations. So 20.14 plus 59.08, and x is 1. So we'd get a value of 79.22. So our xy pair would be 79.22. We can do the same thing with the equation that was calculated without the outlier. And plug in 1 for x, and that would give you 74.15. So our xy pair on that one would be 1, 74.15. So those are our two predictions for x equals 1. So next one, they want to predict y for x equals 2. We just decided that the biggest value of x is 1.4. So 2 is a little bit outside that. So we'll just get into the habit of saying, since that's outside the range, we really shouldn't try to predict y. The range of x provided is from 0.4 to 1.4, and x equals 2 is outside the range. So we shouldn't use it to predict y because it's outside. We don't know what's going to happen to the line after it gets past too much past 1.4. So remember, it could end up starting to go down, or it could go up in some kind of log pattern. We really don't know. So we're just going to not make any predictions if it's past the values of x that are provided. So last topic in regression is called residuals. And residuals are the difference between the predicted value of y for a given value of x compared to the actual value of y that goes with the x. And what we do with residuals is find out if there's any pattern to it, or to all the residuals for a particular data set. So a residual is your observed value of y, which is from your data set, minus the predicted y, which is when you plug x into your equation. And we can use just a plain y for the observed y, so we could also just say that this is y minus y hat. So y hat would be the predicted y. What we're going to do after we calculate residuals is plot them. So plot x on your x-axis and then y minus y hat on your y-axis. And you're trying to make sure that they don't have any pattern. And there's some pictures in your book that show patterns and no patterns that you can take a look at. So for the example, we're going to use the exact same data set here, and I'm just going to do it without the outlier at all. We're just going to do this one time. So let's just get rid of that one. And I'm going to make another, I'm going to make a row called y hat, and I'm going to make another row y minus y hat, which is the residual. So what we're going to do is, for each value of x that's given, we're going to plug that into the equation and solve for y, which is actually now going to be y hat, or predicted y. So the first point in our data, x equals 1. So we're going to say y hat equals 29.57. Remember, this is the equation without the outlier. So our first predicted y, or y hat, is 74.15. And then the next row down is y minus y hat. So we do 76.4 minus 74.15, and the residual for that one would be 2.25. So really what we're doing here, I'm just going to draw a quick sketch. So if we have our line, but our original data points that we used to make the line aren't exactly on the line, the residual is just the distance from the point, the actual observed value, to the predicted value, which is the value on the line for that given value of x. So x here, our observed value is up here at this value of y. Our predicted is the y that's on the line. So the residual, so this is y hat predicted. Our residual is just the distance between them, or the difference between them. So this distance in here that I'm in green is the residual. So this residual of 2.25 that we just calculated means that there's a difference of 2.25 units between the observed y that was used to make the equation and the y that's predicted that's on the line of the equation for that value of x. So let's keep going. We have x equals 0.8. So again, you'd take your equation, and plug in 0.8 for x, and when you solve that, you get 65.23. So I'll put that in the next box, 65.23. And if you subtract these, 67.7, the observed y, minus 65.23, the predicted y, we get 2.47. Next one is 0.9. We're skipping the outlier. And for this one, we get 69.69. So 71.1 minus 69.69, we get 1.41 there. So I'm not going to keep writing the equations out. I'm just going to fill out the rest of the table. So for the rest of them, this next one would get 78.61 if you plug in 1.1 for x, and if you subtract those, we get 0.19. Or sorry, 0.19. Next one, when you solve for y, get 91.98, and that gives us a residual of negative 3.58. And for 0.4, we have 47.70 or 47.40, and a residual of negative 13.5. Make sure you keep track of if they're positive or negative when you subtract, because that's important. Next one, x is 1.2. We get predicted y of 83.07, which gives us a residual of negative 2.57. And just 2 left. We get 60.78 and 3.42. And the last one, for x equals 0.5, if we plug that into the equation, y hat equals 51.86. And the residual will be 5.44. So now we have all of our residuals, and we're going to plot them, scatter plot again. So we're going to use x values on the x-axis and y minus y hat on the y-axis. And our values are going to be above and below 0. So I'm just going to put a line across for 0 in the middle, and then our values for y might be above or below that. And we want to make an even scale. This is just for a demonstration, so it's not going to be perfect here, but we'll just go by 5s and kind of estimate. And then our x-axis, our smallest x is 0.4. So something like this might work. We'll just go by 0.2. So 0.2, 0.4, 0.6, 0.8. Okay, so that should get us good enough for just to show you how this works. So what we're going to do, you could also plug in the values of the residuals into another list in your calculator, and then have your calculator do a scatter plot just like we did before. But just a quick sketch is fine for this as well. So for x equals 1, the residual is 2.25. So I'll use a different color so we can see these. So 1 and 2.25, somewhere around here. So for 0.8, we have 2.47. For 0.9 for x, we have 1.41. 1.1 and 0.19. 1.4 and negative 3.58, somewhere around there. For 0.6, we had 4.48. For 0.4, negative 13.5, that's way down here. And 1.2, negative 2.57. 0.7 and 3.42. And 0.5 has 5.44. So there's our residual plot. Now, what we're looking for is no pattern. And to me, this looks like a linear pattern of residuals. It looks like we have a pattern. And that's a problem. So we wanted there to be no pattern. And what that means is when you make a residual plot that has a pattern, that means that a linear equation actually might not be the best fit or best explanation. So far everything we've done had looked pretty good. We got a significant value for a correlation. got a significant value for the slope. We had a line that looked pretty good, but the residual plot shows a pattern, and that means that maybe we shouldn't rely on this as much as we thought we should as when we were doing the other examples. So don't rely on the equation to make predictions of y hat. Okay, so again, everything looked good up until we got to residuals. It's something that's always good to check when you're doing a linear regression problem. See if there's a pattern in your residuals, and if there is, don't rely too much on the results that you got.